A telescope just revealed something that should not exist. Galaxies fully formed when the universe was barely born. Black holes containing billions of solar masses when there was no time for them to grow. The cosmos we thought stretched 14 billion light-years actually spans 93 billion light-years across. What if everything we believed about the size of the universe was wrong? The James Webb Space Telescope found mature galaxies just 290 million years after the Big Bang. They contain several hundred million times the mass of our Sun. Standard physics says this is impossible. Gravity works slowly. Gas needs time to cool and collapse. Yet there they are. Massive structures stretching millions of light years when the math says they cannot exist. The edge of everything we can observe sits 46.5 billion light years away. Not 14 billion. Space itself has been stretching while ancient light crawled toward us. The oldest photons Webb captured left their source 13.5 billion years ago. Earth did not exist. Our Sun had not formed. The Milky Way was still assembling from scattered clouds of hydrogen. These impossible galaxies harbor supermassive black holes that grew too fast. They exist in a cosmic web of dark matter filaments we are only now beginning to see. The universe is not what we thought. Our fundamental models of physics, time, and cosmic expansion are either incomplete or entirely wrong. If you enjoy what comes next, hit that like button and subscribe. We begin now. Light moves faster than anything in the universe. Confirmed by science. Nothing crosses space more quickly. 186,000 miles every single second. In the time it takes you to blink, a photon could circle Earth 7 times. That speed defines the absolute boundary of reality itself. But here's what most people never consider. Even at that velocity, light needs time to travel, and that simple truth changes everything about how we see the cosmos. Look up at the moon tonight. The glow touching your eyes left the lunar surface 1.3 seconds ago. Not long, barely noticeable. You're seeing the moon as it was a heartbeat earlier. Close enough to call it the present. Close enough to trust what you observe. The sun sits farther away. Its light takes 8 minutes to reach you. When you feel warmth on your skin during a summer afternoon, if that heat departed our star before you stepped outside, if the sun vanished this very moment, you would have 8 minutes of ignorance, 8 minutes of blue sky and birdsong before darkness arrived. When you look at the stars tonight, you're not seeing the universe. You're seeing history. Some of those lights winked out before humans existed, and we're only now receiving their final message. Our nearest neighboring star floats 4 light-years distant. The photons entering your telescope tonight began their journey when a different president held office, when different songs played on the radio. 4 years of silent travel through absolute emptiness before reaching your waiting eye. This is where the strangeness begins. We thought we understood what we were looking at out there. Turns out, we were barely seeing anything at all. Every object beyond our planet exists in the past when we observe it. We have never witnessed the present state of another world, not once in human history. Every galaxy, every star, every distant moon reveals only where it was and what it looked like when its light departed. The night sky is a museum of ghosts, beautiful and ancient and already gone. The James Webb Space Telescope was built to chase the oldest ghosts of all. It orbits 1 million miles from Earth. Out there, beyond the moon's path, it floats in perpetual shadow. Its mirror stretches 21 feet across, coated in gold thinner than a human hair. That golden surface catches photons that have traveled for eons. The universe plays a trick on ancient light. As space expands over billions of years, it stretches light waves like taffy being pulled. Visible colors shift into longer wavelengths. They slide past red, past what human eyes can detect, into invisible infrared. Think of it like a siren passing you on the highway. The sound drops lower as distance grows. Light does the same thing across cosmic distances. It stretches into longer, redder wavelengths as it travels through expanding space. The oldest light in existence has been stretched so far it becomes completely invisible to ordinary telescopes. Hubble could not see these ancient photons. Neither could any ground-based observatory. The earliest chapters of cosmic history remained hidden behind a curtain of invisible wavelengths. We knew light from the infant universe was arriving constantly, washing over our planet every moment. We simply lacked the eyes to perceive it. Our Webb was explicitly designed to pierce that veil. Its instruments detect infrared light with extraordinary precision. Where previous telescopes saw darkness, Webb sees structure. Where we assumed emptiness, Webb reveals form. The telescope transforms invisible radiation into images of things that existed before our solar system took shape. 1 year of light travel covers 6 trillion miles. Write that number down and it loses meaning. 6 trillion miles of empty vacuum crossed by a single photon in 12 months. Multiply that by billions of years and you approach the distances Webb routinely observes. Webb is essentially excavating layers of cosmic archaeology, peeling back time itself with each deeper observation. Every adjustment of its mirror, every subtle change in its instruments, digs through another stratum of history. And closer targets reveal recent epochs. Distant targets reveal the universe's infancy. The telescope moves backward through time simply by looking farther away. This is not metaphor. This is the mechanical reality of observation. Distance equals time. Depth equals history. The farther Webb peers, the younger the universe it witnesses. Most people assume we see things as they currently exist. The intuition makes sense. Open your eyes and the world appears immediate, present, real. But beyond our atmosphere, that assumption collapses entirely. The truth is far stranger. We inhabit a cosmos where the present remains forever hidden beyond the speed of light. The next time you gaze upward on a clear night, remember what you're actually witnessing. Not the universe as it is, the universe as it was. Layers upon layers of ancient light, arriving simultaneously, painting a picture assembled from countless different moments across billions of years. Webb stares into that layered past with unprecedented clarity. It gathers infrared photons, too faint for any previous instrument to detect. It reconstructs images from radiation that departed its source when time itself was young. And when Webb finally turned toward the most distant reaches of observable space, when it captured light from the earliest epochs we can possibly perceive, it found something waiting there that no one predicted. Something was waiting there. Something that violated everything we thought we knew about how the universe assembled itself. In October of 2023, Webb's instruments locked onto a faint smear of infrared light in a region of sky astronomers called Jades. The telescope gathered photons for 10 straight hours. 10 hours of patient collection, catching individual particles of light so sparse they arrived perhaps one every few seconds. When researchers processed the data and confirmed their findings in January of 2024, they found themselves staring at the impossible. The galaxy has a name now. Jades GSZ 14-0. Not poetic, but precise. It sits 13.5 billion light-years away from us. That distance means the light Webb captured left this galaxy when the cosmos was only 290 million years old. In cosmic terms, that's infancy. That's the universe still in its crib. The galaxy stretches 1,600 light-years across. It contains several hundred million times the mass of our star. And those numbers might sound reasonable until you understand what they mean. One astronomer described the discovery this way. Finding this galaxy was like excavating a site from ancient Rome and pulling a smartphone from the dirt. Something far too advanced for its era. Something that has no business being there, yet there it was, buried in the data, undeniable. Here is why this matters. If you compressed the entire 13.8 billion year history of the universe into a single calendar year, this galaxy existed on January 2nd. Everything else happened afterward. Every dinosaur that walked the earth, every human civilization that rose and fell, every moment of recorded history, every breath you have ever taken, all of it fits into the remaining 363 days. This galaxy was already assembled, already massive, already mature on the second day of cosmic time. Webb measured something called redshift to determine the distance. Light stretches as it travels through expanding space, shifting toward redder wavelengths. This galaxy showed a redshift of 14.32. That number placed it firmly in the epoch when stars and galaxies were supposed to be just beginning their slow assembly. Instead, Webb found something that looked ancient, developed, complete. In its first 18 months of operation, Webb extended our view into the cosmic past by 40%. Astronomers expected to find primitive structures in that newly revealed era. Small clumps of gas, proto-galaxies still gathering material, the earliest sketches of what would eventually become the mature structures we see closer to our own time. And they found the opposite. The expected galaxy counts for the early universe were exceeded by a factor of 10, not 10% more than predicted, 10 times more. Where models suggested scarcity, Webb revealed abundance. Where theory demanded simplicity, Webb uncovered complexity. This galaxy should be impossible. That phrase keeps appearing in the scientific papers. Researchers use careful language. They speak of tension with models. They note discrepancies with theoretical predictions. But the underlying message is clear. Our physics cannot account for what Webb found. Gravity works slowly. This is not opinion. This is the mechanical reality of how mass attracts mass across cosmic distances. Gas clouds collapse toward each other at predictable rates. Oh, the mathematics of gravitational attraction have been tested and verified for centuries. We know how fast matter can fall together. Gas needs time to cool. Hot hydrogen radiates energy gradually. It must shed heat before it can condense into dense pockets. Those dense pockets must accumulate more material before they can ignite as stars. This cooling process follows strict thermodynamic rules. We understand the timescales involved. Stars need time to form. Nuclear fusion begins only when pressure and temperature reach specific thresholds. Protostars gather mass for millions of years before lighting up. The first generation of stars could not have appeared instantly. They required the patient accumulation of hydrogen in exactly the right conditions. Add these processes together. Gravity pulls matter inward. A gas cools and condenses. Stars ignite. Those stars live and die, seeding space with heavier elements. New stars form from enriched material. Slowly, incrementally, galaxies assemble themselves from scattered raw ingredients. 290 million years is not enough time. The math does not work. Physics, as we understand it, says these galaxies cannot exist. Yet there they are, captured in infrared light, measured with unprecedented precision, real beyond any doubt. The discovery forced astronomers to confront an uncomfortable possibility. Either the early universe contained mechanisms we have never observed and cannot explain, or our fundamental models of cosmic evolution are flawed. Neither option offers comfort. Both demand a revolution in how we understand the first chapter of existence. These structures assembled from nothing to fully mature systems in cosmological terms, like going from the Ice Age to smartphone civilization in a single heartbeat. No gradual progression, no slow climb up the ladder of complexity, just sudden, inexplicable maturity appearing in an epoch that should have been empty. Webb did not find one anomaly. It found populations of them, entire communities of massive galaxies scattered across the early universe, each one defying the careful predictions of decades of theoretical work, each one sitting where emptiness should have been. If these galaxies exist, what else is wrong with our models? What other assumptions have we carried forward without questioning? The universe breakers demand answers. They challenge the foundations of cosmology itself, and they are only the beginning of what Webb has revealed. But before we go further, we need to address something fundamental, something most people assume they understand, but actually have completely wrong: the size of the universe itself. Here is what seems like simple logic. The universe is about 13.8 billion years old. Light travels at a fixed speed. Therefore, the farthest we could possibly see is 13.8 billion light years away. Anything beyond that distance has not had time to send its light to us yet. The math appears straightforward. Age times speed equals distance. Clean, simple, completely wrong. The actual edge of the observable universe sits not 13.8 billion light years away, not 20 billion, not even 30. The boundary of everything we can ever hope to observe lies 46.5 billion light years from where you are right now. In every direction, multiply that radius by 2. The total diameter of the observable universe spans 93 billion light years across, a number that seems to violate the very rules we just established. How can we see something almost 50 billion light years away if the universe has only existed for 13.8 billion years? The light should not have had time to reach us. The arithmetic should not work, except space itself has been cheating the entire time. Picture a balloon with dots drawn on its surface. small circles scattered randomly across the rubber. If you begin inflating that balloon, something peculiar happens. Every dot moves away from every other dot. But none of them are sliding across the rubber surface. None of them are traveling anywhere. The dots remain perfectly still relative to the material beneath them. What changes is the material itself. The rubber between the dots stretches. The surface grows. Distance increases without motion. Galaxies work the same way. They are not flying through space like bullets fired from the Big Bang. They are sitting relatively still while the fabric of space between them expands. The universe is not a container filled with moving objects. The container itself is growing. This changes everything about how we measure cosmic distances. When light left a distant galaxy 13 billion years ago, that galaxy was much closer to us, maybe 3 billion light years away. The photons began their journey across what seemed like a manageable gulf. But as those photons traveled, the space they were crossing stretched. More distance appeared behind them than they covered in front. By the time that ancient light finally reaches our telescopes, the galaxy that emitted it has been carried outward by the expansion. It now sits 46 billion light years away, even though its light only traveled for 13 billion years. The universe pulled a trick on the light itself. Consider a treadmill. You stand at one end, someone stands at the other, maybe 10 feet away. You start walking toward them. Under normal circumstances, you would reach them in a few seconds. But what if the treadmill accelerates beneath your feet? You walk forward at 3 miles per hour. The belt moves backward at 4. Despite walking toward your target, you actually move away from it. Your effort is real, yet your motion is real, but the ground beneath you defeats your progress. Light faces the same problem across cosmic distances. Photons race toward us at their fixed, unbreakable speed, but the space beneath them expands faster than they can cross it. In the early universe, some photons were effectively running backward on a treadmill that kept speeding up. They moved toward us at the maximum possible velocity, yet the distance between us grew anyway. This is not a metaphor. This is the actual mechanism of cosmic expansion. And here is where the situation becomes genuinely strange. The expansion is not slowing down. Gravity should be pulling everything back together, decelerating the outward rush, gradually bringing the universe towards some equilibrium. That would make intuitive sense. Mass attracts mass. The expansion should be fighting against gravity and losing ground over time. The opposite is happening. The expansion is accelerating. Every year, the space between distant galaxies grows faster than it did the year before. Something is pushing outward with increasing force, overwhelming gravity across cosmic scales. We call this something dark energy, not because we understand it, because we do not. The name is a placeholder for our ignorance. What we know is this: 68% of everything that exists is dark energy. More than 2/3 of the entire universe consists of this invisible force that drives space apart. Regular matter, the atoms that make stars and planets and your body, accounts for less than 5% of reality. Dark matter, the invisible scaffolding that holds galaxies together, it makes up another 27%. But dark energy dominates everything. It is the majority shareholder in existence, and its only apparent function is to make the universe expand faster and faster forever. Let that reality settle for a moment. Most of the cosmos is made of something we cannot see, cannot touch, cannot detect directly, and do not understand. We only know it exists because of what it does to space itself. The edge of the observable universe marks a hard boundary, not because nothing exists beyond it, but because light from those regions has not had time to reach us yet. Some of it never will. The expansion is carrying those distant territories away faster than their light can approach. They are receding beyond any possibility of contact. Yet the universe is simultaneously finite in what we can observe and infinite in what actually exists. That distinction matters. The observable universe, our little bubble of visibility, contains roughly 2 trillion galaxies. That number comes from older estimates. Webb is already suggesting the real count may be significantly higher, but even 2 trillion represents only what falls within our cosmic horizon. Beyond that horizon, more universe continues. How much more? We genuinely do not know. Current models suggest the total universe may be at least 250 times larger than the observable portion. Some calculations indicate it could be infinite. an endless expanse of galaxies and voids and structures we will never detect because their light is permanently out of reach. Every direction you look, and the edge sits 46.5 billion light-years away, not because the universe ends there, because that is where visibility ends. The rest continues into distances we cannot even properly imagine. The photons Webb collects from ancient galaxies began their journey when those galaxies were relatively nearby. Space stretched beneath them for billions of years. The light itself stretched too, its wavelength pulling longer, like a spring being extended. What started as visible light arrived as infrared. What started as ultraviolet arrived as visible. The universe shifted every photon toward the red end of the spectrum simply by growing while the light traveled. This is why Webb sees in infrared, not by choice, by necessity. The oldest light in the universe has been stretched beyond what human eyes could detect. Only instruments sensitive to longer wavelengths can capture these ancient messengers. The 93 billion light-year span represents a hard observational limit. We exist inside a bubble of knowability, surrounded by an ocean of the forever unknown. Galaxies we will never see, structures we cannot map, perhaps other civilizations asking the same questions about their own horizons, wondering what lies beyond the edge of their observable cosmos, never realizing we exist just beyond their line of sight. The numbers defy intuition. They break the simple math we learned to trust, and they reveal something profound about our position in existence. We are not at the center of anything. Asa, we simply occupy one small region where light has had enough time to reach us before space carried its source away. The universe breakers Webb discovered formed in this expanding arena. The impossible galaxies assembled while space itself was stretching between every particle. Their existence challenges not just how fast gravity works, but how structure could form at all in an environment constantly pulling itself apart. And the expansion continues accelerating. The dark energy that dominates reality shows no sign of weakening. If anything, its influence grows stronger as more space appears for it to fill. The acceleration continues. Dark energy stretches the void between galaxies wider with each passing moment. But something else lurks in that early darkness, something that should not exist. Of 430 million years after the Big Bang, a black hole sat at the heart of Galaxy G N-Z11. Not a small black hole, not a modest one, a monster weighing billions of times more than our Sun. Webb found it waiting there, impossibly heavy, impossibly old. This is where physics breaks down. Normal black holes form when massive stars die. A star needs about 20 times the mass of our Sun to collapse into a black hole at the end of its life. The resulting black hole typically weighs somewhere between 10 and 100 solar masses. It then grows slowly over cosmic time, pulling in surrounding gas, swallowing smaller objects, gradually accumulating weight over billions of years. The black hole in GNZ11 did not have billions of years. It had 430 million. That gap matters enormously. Imagine arriving at a crime scene where a skyscraper appeared overnight. No construction crews anywhere. No materials on site. No permits. No plans. No evidence of how it was built. Just an impossible structure standing where empty ground existed hours before. You would have to work backward from the impossible result to find the culprit. That is exactly what astronomers face with these ancient black holes. The math simply does not work. Even if a black hole formed from the very first generation of stars and began consuming matter immediately, it could not reach billions of solar masses in that time frame. The physics of gas falling into black holes sets a maximum feeding rate. Radiation pressure from the infalling material pushes back against further accretion. There is a speed limit on cosmic gluttony, yet there it sits, as a gravitational behemoth from an era when the universe itself was barely forming its first structures. Should be impossible, and yet undeniably real. Webb did not stop there. When the telescope turned its infrared gaze toward Galaxy G S3073, it found something equally strange. Not a black hole this time, a chemical signature. The ratio of nitrogen to oxygen atoms measured 0.46. That number means nothing in isolation. In context, it screams. Every atom of carbon in the early universe came from stellar interiors. Every atom of oxygen, every atom of nitrogen. These elements did not exist at the beginning. Hydrogen and helium dominated the cosmos after the Big Bang. Everything heavier had to be forged in the cores of stars, then scattered into space when those stars died. So the strange nitrogen ratio in GS3073 suggests something happened before. An earlier unseen generation of stars must have lived and died almost immediately after the universe began. Stars we have never directly observed, stars that left behind only chemical fingerprints in the generations that followed. Theorists call them population 3 stars, the first fires in an infinite darkness. These would not have been stars like our Sun. They could not have been. Population 3 stars formed from pure hydrogen and helium, the only elements available. Without heavier atoms to help gas clouds cool efficiently, gravity had to work with much larger masses to trigger collapse. The result would have been stellar furnaces 1,000 to 10,000 times the mass of our Sun. Picture that scale. Our Sun contains 99.8% of all the mass in our solar system. Every planet, every moon, every asteroid combined makes up less than a fraction of a percent. Now, multiply that stellar mass by 10,000. These monsters would have been cosmic furnaces burning so hot and fast they lived mere millions of years before exploding. They seeded the cosmos with the heavy elements needed for everything that followed. This is the part that gets me. These monster stars, if they existed, burned and died before anything we would recognize as a galaxy even formed. They were the first fires in an infinite darkness, and they left behind the ashes from which we are made, the nitrogen in your muscles, the oxygen in your lungs, the carbon in your cells. All of it passed through stellar cores before Earth existed. Some fraction may trace back to those primordial giants. When a population 3 star died, it did not go quietly. These behemoths likely collapsed directly into black holes, skipping the normal stages of stellar death entirely. No neutron star remnant, no gradual fade, just sudden, catastrophic implosion, creating a black hole seed potentially thousands of times more massive than anything formed from later stellar generations. Those seeds would have had a head start, billions of years of head start compared to black holes forming through conventional channels. Suddenly, the impossible masses at GNZ 11 become slightly less impossible, not comfortable, not explained, but at least approached. Other suspects remain in this cosmic whodunit. Some theorists propose direct collapse black holes, as where enormous gas clouds skipped the star phase entirely and collapsed straight into black holes, weighing 100,000 solar masses or more. Others suggest primordial black holes formed from density fluctuations in the first moments after the Big Bang itself. The chemical evidence points toward population 3 stars as the prime suspect, but we have never directly observed one. They existed too briefly, too early, too far away. We see only their legacy in the strange ratios of elements scattered through ancient galaxies. Their deaths would have been spectacular beyond imagination. When these titans exploded, they outshone anything in the modern universe. Not just stars, entire galaxies. Consider a quasar, the brightest sustained objects in existence. A quasar forms when a supermassive black hole actively devours surrounding matter. The infalling material heats to millions of degrees before crossing the event horizon, releasing torrents of radiation across the electromagnetic spectrum. A single quasar can emit light equivalent to 1 trillion stars burning simultaneously. Webb measured one quasar at 600 trillion stellar luminosities, 600 trillion suns concentrated in a region smaller than our solar system. That output would make the quasar visible across most of the observable universe. And the engine driving that brilliance is a black hole that should be impossible. But there it burns, a beacon from an era we are only beginning to understand. The black holes grew too fast. The chemical ratios appeared too quickly. The luminosities reached levels that strain our models of how matter and energy interact. Each discovery deepens the mystery rather than solving it. Something happened in those first few 100 million years. Processes we have not identified. Physics we have not mapped. The monster stars may be part of the answer. Direct collapse, black holes may contribute. Dark matter concentrations we cannot directly observe may have channeled gas into the right configurations at the right moments. Whatever built these cosmic engines left no instruction manual, only the engines themselves, still running, still visible across billions of light years. waiting for us to reverse engineer their creation from nothing but the light they emit and the elements they scattered. The monsters in the dark seeded everything that followed. As they forged the raw materials, they created the gravitational anchors. They set the conditions for the galaxies, stars, and planets that would eventually produce life capable of looking back and wondering how any of it happened. Everything we have discussed depends on a single technique. Every claim about distant galaxies, every measurement of cosmic age, every assertion about what existed when time was young, all of it comes down to reading stretched light. The universe communicates through light, and light carries information in ways we are still learning to decode. When astronomers point Webb toward the ancient cosmos, they are not simply collecting photons. They are intercepting messages written in wavelengths, messages that have been altered by their journey across billions of years of expanding space. Light has a signature. Every element in existence produces a unique pattern when it emits or absorbs radiation. Hydrogen creates specific lines at specific wavelengths. Oxygen leaves different marks. Nitrogen, carbon, helium. Each writes its name across the electromagnetic spectrum in a way that cannot be forged or mistaken for another element. Scientists call these patterns spectral fingerprints. Spectroscopy is the technique that reads these fingerprints. It works like passing light through a prism. White light separates into its component colors because different wavelengths bend at different angles. A prism reveals the rainbow hidden inside what appears to be colorless light. Astronomical spectroscopy does the same thing at vastly greater precision. When Webb captures light from a distant source, it splits that light into thousands of individual wavelengths. The resulting spectrum shows bright lines where elements are emitting radiation and dark lines where they are absorbing it. The pattern reveals exactly what chemicals exist in that distant object. But something else appears in those patterns, something unexpected. The fingerprints are in the wrong place. Hydrogen has a distinctive emission line in ultraviolet light at 92 nanometers. This wavelength falls far outside what human eyes can see. When scientists examine light from the most distant galaxies, they find that same hydrogen signature. The pattern matches perfectly. The spacing between lines is correct. The relative brightness is right. The fingerprint belongs to hydrogen. But it appears at 1380 nanometers. At that wavelength sits deep in the infrared. The light has been stretched by a factor of 15. What started as invisible ultraviolet has become invisible infrared, pushed across the entire visible spectrum and beyond, without ever being something our eyes could detect. This stretching happens because space itself expanded while the light was traveling. Think of sticking your hand out of a car window. As the car speeds up, you feel the wind change. It stretches and pulls at your fingers differently than when you were moving slowly. Light experiences something similar as it crosses expanding space. The wavelength itself gets pulled longer, not because anything is pushing on the photon, but because the fabric it travels through is growing. The amount of stretching tells astronomers exactly how much space expanded during the journey. A factor of 15 means space grew 15 times larger between the moment that light left its source and the moment it reached Webb. That stretching correlates directly with distance and time. Ancient light from the earliest epochs arrives stretched by factors of 14 to 16 times its original wavelength. Light that left a galaxy when the universe was young has been pulled so dramatically that every wavelength shifted into ranges telescopes could not see for decades. The Hubble Space Telescope operates primarily in visible and near-infrared light. It could not detect most of this ancient radiation because the radiation no longer exists in wavelengths Hubble can capture. Here is what makes this strange. The early universe was not dim. Galaxies blazed with newborn stars. Quasars burned with intensities we struggle to comprehend. The cosmos glowed with energy across every wavelength. But all that visible light has been stretched into infrared over billions of years. The universe was hiding in plain sight. Webb operates in a range from 0.6 to 28 microns. That spans from the edge of visible red light deep into the mid-infrared. This range captures precisely the wavelengths where ancient light has landed after its long journey through expanding space. Webb does not see farther because it has a bigger mirror. It sees farther because it looks in wavelengths where the oldest light now exists. The specifics matter. When scientists measure a distant galaxy and report a high redshift value, they are describing exactly how much the light stretched. They find the hydrogen fingerprint, and they note its current wavelength. They calculate the ratio between where it appears and where it should appear if space had not expanded. That ratio becomes the redshift number. Higher redshift means more stretching. More stretching means longer travel time through expanding space. Longer travel time means the light originated earlier in cosmic history. The math connects wavelength shift directly to cosmic age. This technique transformed astronomy from speculation into measurement. Before spectroscopy, astronomers could observe distant objects but could not determine their true distances with precision. They could not know whether a faint galaxy sat relatively nearby or impossibly far away. Brightness alone does not reveal distance because a dim, nearby object and a brilliant distant object can appear identical in photographs. Yet spectroscopy changed everything. The fingerprints cannot lie. If hydrogen appears at 1380 nanometers instead of 92, the stretching factor is fixed. The distance follows from known physics. The cosmic age follows from the distance. One measurement unlocks everything. Webb carries multiple spectrographs designed for different purposes. Some capture broad ranges of wavelengths simultaneously. Others focus on narrow bands with extreme precision. Together, they can analyze light from thousands of objects in a single observation, measuring redshifts and chemical compositions across vast swaths of the ancient universe. The process requires patience. Faint light means long exposures. Long exposures mean careful calibration. Careful calibration means comparing observations against known standards. Every measurement gets checked against the fingerprints we have studied in laboratories here on Earth. Hydrogen behaves the same way everywhere in the universe. The physics does not change with distance. This reliability makes spectroscopy the foundation of modern cosmology. Every claim about cosmic scale rests on trusting that atomic physics works identically across space and time. Every measurement assumes that hydrogen in a galaxy 13 billion years ago emitted the same wavelengths as hydrogen in a laboratory today. That assumption has been tested countless ways. It holds. When scientists say they found a galaxy that existed when the universe was young, they are not guessing based on how faint it appears. They are calculating based on exactly how far its light has been stretched. When they report chemical compositions in ancient stars, they are reading the fingerprints directly, matching shifted patterns to known elements. The technique reveals what the universe was doing when that light departed. It shows which elements had formed by that epoch. It indicates how hot the gas was, how fast it was moving, whether it was falling inward or flowing outward, all encoded in the positions and shapes of spectral lines. Light becomes a time machine when you know how to read it, and Webb was built specifically to read light that has traveled farther and stretched more than anything previous telescopes could detect. The infrared capability is not a bonus feature. It is the entire point. Without it, the earliest epochs remain invisible, regardless of how powerful the telescope might be in other wavelengths. And this is how we know what we know, not through imagination, not through assumption, through the precise science of measuring stretched wavelengths and calculating what that stretching reveals about distance, time, and composition. The method has been refined across generations. The instruments have grown more sensitive. The measurements have become more accurate. And through those measurements, patterns have emerged across the cosmic web that no one predicted. Patterns have emerged across the cosmic web that no one predicted. And that phrase itself holds a secret. The cosmic web is not a metaphor. It is the literal structure of the universe, a scaffold of invisible matter connecting everything to everything else across distances your mind cannot hold. Pull back from any single galaxy. Pull back from clusters of galaxies. Pull back far enough, and a pattern reveals itself. Matter does not scatter randomly through space. It organizes. It connects. It flows along channels that stretch for hundreds of millions of light years. The universe has architecture. Dark matter built this architecture. 85% of all matter in the universe is dark matter, not the atoms that form planets and stars and your own body. Something else entirely. It does not emit light. It does not absorb light. It does not interact with ordinary matter except through gravity. Yet it outweighs everything you can see by a ratio of nearly 6-1, confirmed by science. Not through direct observation of dark matter itself, through what it does to everything around it. Galaxies move in ways that make no sense unless invisible mass surrounds them. Light bends around apparently empty space as if something massive were there. The evidence accumulated for decades until the conclusion became unavoidable. The universe contains a hidden component that shapes everything visible. Picture water flowing downhill into valleys. The rain falls everywhere, but it does not stay everywhere. It runs along the path of least resistance. It gathers in low points. It carves channels over time. Now imagine this happening across the entire universe, except the valleys are regions where dark matter concentrates. The water is ordinary matter, hydrogen, helium, the raw material for stars. Where dark matter pools, gravity pulls harder. Ordinary matter falls toward those denser regions. Stars form. Galaxies coalesce. The invisible shapes the visible. The hidden determines the seen. As this flowing creates structure, filaments of dark matter thread through the cosmos like blood vessels through a body. Galaxy clusters mark the densest nodes where multiple filaments intersect. Between the filaments stretch vast empty regions where almost nothing forms. The universe looks less like a uniform scattering of stars and more like a web spun by something impossibly large. Consider the scale of just one strand in this web. The local group of galaxies sits on a filament 110 million light-years across. Your entire galaxy, the Andromeda Galaxy, dozens of smaller companions, all perched on one thread of the cosmic web, one filament among countless millions. The nodes where filaments meet hold even more mass. A typical galaxy cluster contains between 100 and 1,000 galaxies bound together by shared gravity. Not just gravity from the galaxies themselves, gravity from the dark matter they all share. One massive cluster contains approximately 100,000 billion times the mass of our star. Written out, that is a 1, followed by 14 zeros. More matter concentrated in a single cosmic node than your mind can meaningfully grasp. Yet the Coma cluster sits 321 million light-years away. Astronomers studied it for decades. The galaxies within it move too fast. They should fly apart based on visible matter alone. Something invisible holds them together. Dark matter filaments are like highways connecting cosmic cities. The cities are galaxy clusters. The highways themselves remain invisible, made of matter we cannot see directly, but the traffic flowing along them reveals where the roads must be. Galaxies line up along paths that trace invisible channels. Their positions mark routes drawn by something hidden. Webb has begun mapping these highways. In the ancient universe, long before the cosmic web fully formed, protostructures already existed. One discovery stands out. A formation called the Cosmic Vine stretches 13 million light-years long and 650,000 light-years wide. For reference, your entire galaxy spans only 100,000 light-years across. The vine is over 60 times wider than everything you call home. Within that single structure sit 20 closely packed galaxies containing 260 billion stellar masses. 20 galaxies in one formation, already organizing along what would become a filament, already following the invisible scaffold of dark matter laid down in the earliest moments. The scaffold itself formed from almost nothing. Quantum fluctuations in the first fraction of a second after the Big Bang created microscopic variations in density, regions slightly denser than average, regions slightly emptier. These variations were smaller than atoms when the universe was young, but the universe expanded. Those atomic scale differences expanded too. What was microscopic became cosmic. Regions of slightly higher density attracted more matter. Regions of slightly lower density lost what little they had. Over billions of years, the structure amplified. The web emerged. Galaxies do not fly through space randomly. They flow along invisible tracks laid down when the universe itself was smaller than a grain of sand. The structure of everything you can see was essentially predetermined by density fluctuations that quantum physics produced before atoms even existed. Every galaxy you have ever seen in photographs, every star in the night sky, every planet circling every distant sun, all of them sit on filaments or cluster nodes or fall toward them along predetermined paths. The randomness is an illusion. The architecture was set before there was anything to build with. This is not speculation. Webb photographs confirm it. The early universe already shows protostructures forming along lines that match where dark matter simulations predict concentrations should exist. The invisible scaffold was already guiding matter into channels when the universe was less than 1 billion years old. The web was already weaving itself. 1,678 galaxy groups catalogued in a single web survey, each group representing a node or a strand, each group revealing how matter organized itself across 12 billion years of cosmic history. The data overwhelms. The patterns emerge anyway. The highways carry traffic toward the cities. Galaxy clusters grow denser as matter flows along filaments toward the nodes. The nodes grow more massive. Their gravity reaches further. More matter falls in. A feedback loop that built the largest structures in existence. But the web has gaps. Between the filaments lie regions where dark matter never concentrated, where ordinary matter never collected, where nothing formed at all. These cosmic voids represent the opposite of everything we have discussed. The spaces between the threads, the emptiness between highways. What happens in those voids shapes our understanding of the universe just as much as what happens in the clusters, perhaps more. The voids between filaments stretch across unimaginable distances, empty, silent, containing almost nothing at all. But before we explore that emptiness, consider what fills the spaces between the voids. Consider what Webb actually found when it pointed at a single patch of darkness and refused to look away. 250 hours. That is how long Webb stared at one region of sky. Not a few minutes, not a single night. Nearly 11 straight days of continuous observation, the telescope's instruments gathering every photon that fell upon its golden mirror. The region it chose was small, slightly larger than 3 full moons placed side by side, a speck against the vastness of the night sky. The kind of patch you would ignore entirely if you were stargazing from your backyard. To build the final image, Webb captured 10,000 individual exposures, 10,000 separate photographs layered and combined, each exposure catching light that had traveled for billions of years, each exposure revealing objects too faint for any previous instrument to detect. Hubble looked at this same region years ago. The older telescope found 10,000 galaxies in that small patch, 10,000 island universes, each containing billions of stars. At the time, astronomers considered this number staggering. The darkness between stars was not empty. It was filled with ancient light from distant worlds. Webb looked at the same patch and found 797,942 galaxies. Actually, let me slow down on those numbers. 797,942 galaxies in one tiny patch of sky, each galaxy with hundreds of billions of stars. The math becomes meaningless after a certain point, yet your brain just stops processing it as real. That is nearly 80 times more than Hubble found. The same piece of sky, the pam-beam darkness between visible stars. But Webb sees in infrared. Webb sees the ancient light that stretched beyond what Hubble could detect. The universe did not suddenly create more galaxies. They were always there. Hubble simply could not see them. Consider the difference in scale. If Hubble's deep field image was printed on a standard sheet of paper, Webb's version would cover an entire wall, 13 feet tall, 13 feet wide, a wall-sized mural of cosmic history, each tiny point a galaxy containing billions of stars and countless worlds. You could spend a lifetime examining that mural and never look at the same galaxy twice. So the dark patches that Hubble saw as empty were teeming with nearly 800,000 galaxies hidden only because their light had stretched beyond detection. The universe was always this crowded. We simply lacked the eyes to see it. The old estimates followed from Hubble's observations. 200 billion galaxies scattered across the observable universe. That number seemed impossibly large. 200 billion separate collections of stars, each one a city of suns. Our own galaxy contains roughly 200 billion stars. The old estimate suggested the observable universe held as many galaxies as the Milky Way holds stars. Those estimates are now obsolete. If Webb finds 80 times more galaxies in every patch it examines, the total count across the entire sky climbs towards something unprecedented. And not 200 billion, potentially trillions, perhaps 10 trillion galaxies, perhaps more, each one containing hundreds of billions of stars, each star potentially hosting planets. The old estimate for planets in the observable universe was 400 quintillion. That is a 4 followed by 20 zeros. Already a number beyond human comprehension. Already more worlds than grains of sand on every beach on Earth. With Webb's revelations, that estimate multiplies. 4,000 quintillion planets, a 4 with 21 zeros trailing behind it. 4 sextillion worlds scattered across the observable cosmos, each one a place, each one with its own geology, its own chemistry, its own history, stretching back billions of years. Most of these worlds are barren, gas giants with crushing atmospheres, frozen rocks spinning around dying stars, worlds too hot or too cold or too irradiated for anything we would recognize as life. But even if only 1 in a million hosts conditions suitable for biology, the number of potentially habitable worlds exceeds comprehension. Webb has catalogued 1,678 distinct galaxy groups from its surveys. Each group represents a cluster of galaxies bound together by gravity. These groups span cosmic history from 12 billion years ago to just 1 billion years ago, 11 billion years of galactic evolution captured in a series of observations. Each group reveals how galaxies clustered, merged, and grew across deep time. The data accumulates faster than astronomers can process it. Every Webb observation reveals more structure, more galaxies, and more complexity hidden in what appeared to be empty darkness. The universe keeps revealing itself as larger, older, and more populated than our models predicted. Picture yourself standing in a field at night. You see a few thousand stars with your naked eye. Then someone hands you binoculars. Suddenly, you see 10,000 more. Then a telescope reveals 100,000. Then a larger telescope shows millions. Each improvement in vision reveals that the darkness was never truly dark. It was filled with light too faint to detect. Webb represents a leap beyond simple magnification. It sees wavelengths invisible to human eyes. It detects light that left its source when the universe was young. Every improvement reveals the same truth. The emptiness was an illusion created by our limited senses. 797,942 galaxies in one patch of sky. Multiply that across the entire celestial sphere. Factor in the regions Webb has not yet observed. Account for the galaxies too distant, even for infrared detection. The number keeps growing. 4,000 quintillion planets. Worlds of rock and ice and gas. Worlds with one sun, or 2, or 3. Worlds orbiting close to their stars and worlds frozen in the outer darkness. Worlds that formed recently and worlds older than Earth by billions of years. Somewhere among that vast count, other eyes may be looking up at their own night sky, wondering if anyone else exists. The probability shifts with each new observation, not the probability of extraterrestrial life. We cannot calculate that. We have exactly one data point. Life exists here. Is whether it exists anywhere else remains unknown. What shifts is the probability that habitable conditions exist somewhere else. More galaxies means more stars. More stars means more planets. More planets means more chances for the right combination of temperature, chemistry, and stability. The universe provides countless opportunities. What nature does with those opportunities remains the deepest mystery. Even with these dense fields mapped, vast regions contain nothing at all. The cosmic web has threads, but it also has gaps. Between the filaments where galaxies cluster, other regions stretch for hundreds of millions of light years with almost no matter at all. The voids, the empty spaces between the highways. What those voids reveal about the universe may matter as much as what the crowded regions show. The cosmic web stretches across the universe in delicate threads. Galaxies cluster along those threads like dewdrops on a spider's silk. But between the threads, something else exists. Nothing. The voids. We speak of empty space casually, the gap between planets, the distance between stars. Those regions feel empty to us. They are not. Compared to the cosmic voids, those spaces overflow with matter. The solar system seems crowded. The gulf between galaxies seems dense. The voids are different. They contain less than 10% of the average matter density of the universe. Picture that. Take all the gas, dust, and scattered atoms floating through normal space. Reduce that amount by 90%, then reduce it again. What remains barely qualifies as something rather than nothing. The largest known void stretches 1 billion light-years across. That single empty region takes up 1% of the entire observable universe. 1% of everything we can see, claimed by emptiness. Let that distance settle into your mind. 1 billion light-years. If you began at one edge and traveled at the speed of light itself, the fastest anything can move, you would journey for 1 billion years before reaching the other side. 1 billion years of crossing nothing. 1 billion years of darkness extending in every direction. 1 billion years of silence. Your entire journey would reveal almost nothing to see. This is the cosmic desert. Stand at its center in your imagination. Turn slowly. Look in every direction. Darkness. Not the darkness of night with hidden stars waiting to be revealed, and not the darkness between galaxies where faint light still travels. This darkness holds almost nothing to discover. Tens of millions of light years would pass before you spotted the nearest galaxy. Tens of millions. The Milky Way spans roughly 100,000 light years. You would cross hundreds of Milky Way diameters before finding anything at all. Any companion. Any light source. Any matter. The absence extends beyond stars. It extends beyond galaxies. It extends beyond everything we associate with existence. Silence beyond silence. Emptiness beyond emptiness. The void does not feel like the absence of stars. It feels like the absence of everything. Consider a civilization born there. Imagine their world orbiting a solitary star, somehow drifting through that cosmic desert. They develop eyes, and they develop telescopes. They look up. What would they see? Almost nothing. Perhaps their own star. Perhaps one or two ancient galaxies hovering impossibly far away at the edge of detection. They would map their sky and find it barren. They would search for neighbors and find none. Their astronomers would conclude that the universe was mostly empty, that darkness dominated existence, that matter was rare and precious and isolated. They would have no reason to think otherwise. They would be wrong. Beyond their cosmic desert, the web of galaxies stretches in every direction, clusters containing hundreds of galaxies, filaments connecting those clusters across billions of light years, trillions of stars, countless worlds. Life, perhaps, scattered throughout the crowded regions, none of it visible from the void. And that civilization would look out at their sky and conclude they were alone in an infinite darkness. They would have no way of knowing that the universe teemed with light and matter and complexity just beyond their horizon. The desert would define their understanding of existence. We are fortunate. Our solar system sits within a filament. We look out and see the Milky Way crowded with stars. We point our telescopes deeper and find galaxies everywhere. Our view of the cosmos includes abundance, but abundance is not universal. The voids teach us something else. Scientists discovered that these empty regions serve an unexpected purpose. They function as pristine laboratories. The cosmic web complicates measurements. All that matter bends light. All those galaxies create gravitational noise. All that complexity masks the underlying behavior of space itself. The voids strip away that complexity. With almost no matter to interfere, researchers can study the pure expansion of space. They can watch the universe stretch without contamination from nearby objects. The void reveals what the filaments hide. Dark energy drives the expansion of everything. We know it exists. We measure its effects. But understanding how it works requires clean observations. The voids provide exactly that. The universe's hidden engine laid bare. Where nothing exists, something fundamental reveals itself. These empty regions span 1 billion years of travel. They separate the clusters where galaxies form. They divide the filaments where matter gathers. They create boundaries within the cosmic web, yet they are not barriers. A light crosses them. It enters a void from one side and emerges from the other. The photons traveling through that emptiness experience the expansion of space directly. No gravity wells slow them. No matter deflects them. They sail through 1 billion light years of nothing, and as they cross, they change. The expansion stretches those photons. The wavelength grows longer. What entered as one color emerges as another. The void transforms light through the simple passage of time and distance. This transformation happens everywhere light travels, through the crowded filaments and through the empty voids alike. The journey itself alters what arrives. The universe reshapes every photon that crosses it. Light traveling through both the crowded regions and the empty regions undergoes the same fundamental process. You see, the stretching continues. The wavelengths lengthen. The colors shift toward the invisible. The light changes as it crosses the cosmos. The wavelengths stretch. The colors shift. Every photon carries the signature of its journey through expanding space. but the journey ends somewhere. That somewhere is usually a cluster. Galaxy clusters are the largest gravitationally bound structures in the universe. They are where the cosmic web's filaments converge, where matter pools into concentrations so massive they warp the surrounding space itself. A single cluster can contain anywhere from 100 to 1,000 galaxies, not scattered randomly, but bound together by gravity into a single cosmic system. Each galaxy holds billions of stars. Each star potentially hosts planets, and the cluster holds them all in an invisible gravitational embrace that has persisted for billions of years. The mass involved defies comprehension. A typical massive cluster contains approximately 100,000 billion times the mass of our star. That number is almost impossible to grasp. 100,000 billion. Written out, it is a 1 followed by 14 zeros. If you tried to count to this number at a pace of 1 digit per second, never stopping to eat or sleep or breathe, it would take longer than the current age of the universe to finish. You would count through every moment since the Big Bang and still have numbers left to go. That is the weight of a single cluster. And the weight comes from more than just the galaxies you can see. The stars and planets account for only a fraction of the total mass. Between the galaxies, filling the vast spaces that separate them, exists something called the intracluster medium, hot plasma, gas heated to temperatures exceeding tens of millions of degrees, so hot that atoms lose their electrons entirely and drift as charged particles through the darkness. This plasma makes up 10 to 15% of the cluster's total mass, more mass than all the galaxies combined. You cannot see it with ordinary telescopes. It does not emit visible light, but it glows fiercely in X-rays, betraying its presence to instruments sensitive to those wavelengths. The Coma cluster demonstrates this scale perfectly. It sits 321 million light-years from Earth, not as distant as the ancient galaxies at the edge of observable time, but far enough that its light has been traveling since before anything resembling modern humans walked the Earth. The Coma cluster contains 10,000 trillion stellar masses. 10,000 trillion. The plasma drifting between its galaxies outweighs all the stars visible within them. The cluster itself spans millions of light-years across. If our solar system were placed at one edge, we would have no way of knowing we were inside a cluster at all. The scale would be too large to perceive. These structures formed slowly. Gravity pulled matter together over billions of years. Small groups merged into larger groups. Larger groups fell into clusters. Clusters grew by consuming everything that wandered too close. The process continues today, though on timescales that make human civilization seem like a single heartbeat. The galaxies within a cluster do not sit still. They orbit the cluster's center of mass, tracing paths that take hundreds of millions of years to complete. They pass each other. Sometimes they collide. When galaxies collide, stars rarely hit each other directly. The spaces between stars are simply too vast, but the galaxies themselves distort and merge, their shapes twisting into new configurations over millions of years. Our own galaxy is not immune to this process. The Andromeda galaxy sits roughly 2.5 million light-years away. It is the nearest large galaxy to the Milky Way. On a clear night, far from city lights, yet you can see it as a faint smudge against the darkness. That smudge contains 1 trillion stars, and it is moving toward us. Andromeda approaches the Milky Way at 250,000 miles per hour. This is not the expansion of space carrying it along. This is true motion, real velocity. The galaxy is falling toward us through space itself, pulled by our mutual gravity across the void that separates us. In 4 billion years, the Milky Way and Andromeda will collide. The collision will take millions of years to complete. Stars will pass between stars without touching, but the gravitational interactions will fling some stars out into intergalactic space forever. The spiral arms of both galaxies will unwind. New bursts of star formation will ignite as gas clouds compress against each other, and the night sky will transform entirely. Eventually, after perhaps 1 billion years of cosmic merging, a single elliptical galaxy will remain. No more spiral arms, no more distinct structure, just a vast collection of stars settling into new orbits around a combined center. Whatever observers exist on Earth at that time will see a different universe than we see tonight. They will look up at a sky dominated by this new, merged galaxy. They will have no Andromeda to point toward, no spiral companion approaching through the dark. The cosmic web we have mapped is not frozen. It is not a static structure preserved in time. It moves, it evolves, it consumes itself through mergers and collisions that unfold across timescales we cannot experience. The clusters grow heavier. The filaments shift. The voids expand as matter drains away from them. Every measurement we make captures a single frame of a cosmic movie playing at speeds too slow for any human lifetime to perceive. We see the current arrangement and assume permanence. But nothing about this structure is permanent. Everything is in motion. The clusters are falling toward larger structures. Those larger structures are part of even bigger patterns. Superclusters connect to form walls and sheets of matter that span billions of light years. And all of it moves, driven by gravity and resisted by the expansion of space itself. Attempts to measure exactly how fast all of this structure is moving apart have revealed something unexpected. The measurements do not agree with each other. Different methods produce different answers. And the gap between those answers suggests that something fundamental about our understanding of the universe may be wrong. Something is wrong with our rulers. For decades, scientists have measured the expansion of the universe using two different methods. Both methods are precise. Both have been verified repeatedly. Both should give the same answer. They do not. The first method looks backward in time. Scientists study the cosmic microwave background, the ancient light left over from when the universe first became transparent. This light has traveled for nearly the entire age of the cosmos. By analyzing its patterns, scientists can calculate how fast space was expanding in those early epochs. The number they find is 67 kilometers per second per megaparsec. A megaparsec is roughly 3.26 million light years. So for every 3.26 million light years of distance between 2 points in space, those points are drifting apart at 67 kilometers every second. This measurement comes from the earliest light we can observe. It represents the universe as it was, captured in radiation that predates every star you see tonight. The second method looks at the universe as it exists now. Scientists observe a specific type of supernova, explosions so consistent in their brightness that they serve as cosmic measuring sticks. By tracking how fast these supernovae appear to recede from us, scientists can calculate the current rate of expansion. The number they find is 73 kilometers per second per megaparsec. The gap between these measurements is 6 kilometers per second per megaparsec. That might sound small. It is not. Picture two people measuring the same room with two different rulers. One person says the room is 10 meters long. The other says 11. You check both rulers against a standard meter stick. Both rulers appear accurate. You ask them to measure again, more carefully. They do. Same results. 10 meters, 11 meters. The room cannot be both lengths. Yet here you are, standing in a room that somehow measures two different sizes depending on which tool you use. The rulers are not broken. The room is not changing. Something else must be wrong. Something about your understanding of measurement itself. This is where cosmology finds itself tonight. Both methods have been tested exhaustively. The cosmic microwave background measurements come from satellites that mapped the entire sky with extraordinary precision. The supernova measurements come from telescopes that have tracked thousands of stellar explosions across billions of light years. Neither team has found errors in their calculations. Neither team has found flaws in their instruments. The statistical margins are tight enough that the gap cannot be random noise. The numbers simply do not match. Scientists have a name for this disagreement. They call it the Hubble tension. The word tension captures something important. This is not a small discrepancy that will resolve itself with better data. This is a fundamental conflict between two pillars of modern cosmology. The early universe says one thing, the late universe says another. They cannot both be right. Yet neither appears to be wrong. The uncomfortable truth emerging from this tension is that the problem may not be with our measurements at all. The problem may be with our physics. Think about what that means. Our equations describe how space expands. Our models predict how galaxies form, how light stretches, how the universe evolves across billions of years. These models have proven remarkably successful. They predicted the cosmic microwave background before we detected it. They predicted the distribution of galaxies before we mapped it. They have been tested against observation after observation. And now they produce two contradictory answers for the same fundamental property of the cosmos. Either our understanding of the early universe contains a flaw we have not identified, or our understanding of the late universe contains a flaw we have not identified, or there is some unknown physics affecting expansion that we have not yet discovered, some process, some force, some property of space itself that our equations do not capture. The 6-kilometer gap suggests our fundamental model of the cosmos has a crack in its foundation. This should be impossible. Our physics, refined across a century of observation and experiment, should not produce contradictions like this. We should be able to measure a single property of the universe and get a single answer. The equations should work, but the universe has never cared what should be possible. It simply is what it is. So which measurement is wrong? The terrifying answer is possibly neither. Or possibly our entire framework for understanding how space expands is missing something fundamental. And if that is true, what else are we wrong about? Scientists have proposed explanations. Perhaps dark energy, the force driving expansion, has not remained constant throughout cosmic history. Perhaps it was weaker in the early universe and stronger now. That could explain why the expansion rate appears different depending on when you measure it. Perhaps there is a form of matter we have not detected, something that influenced the early cosmos, but faded away before the present day. Perhaps the cosmic microwave background has been misinterpreted in some subtle way we have not recognized. None of these proposals have gained consensus. None have been confirmed by observation. The tension remains unresolved. Yet what makes this particularly haunting is the precision involved. This is not a case where two rough estimates disagree. These are the most carefully measured values in all of cosmology. Teams have spent decades refining their techniques, eliminating sources of error, cross-checking their results against independent observations. The measurements are extraordinarily good. That is precisely why the disagreement matters so much. If the measurements were sloppy, the gap could be dismissed as noise. But the measurements are not sloppy. They are among the most accurate in all of science. And they disagree. The James Webb Space Telescope is now providing new data that may help resolve this tension, or it may deepen it. Webb can observe supernovae at greater distances than ever before, extending the late universe measurements further back in time. It can study the cosmic microwave background with new instruments. It can search for evidence of unknown physics affecting the expansion of space. But Webb may also discover that the tension is real, that our physics is incomplete, that the universe operates according to rules we have not yet written down. For now, the gap remains. 67 kilometers per second per megaparsec from the early universe, 73 from the late universe. Two rulers measuring the same cosmos, two answers that cannot both be correct. The crack in our foundation is not closing, and something must be filling the space between what we measure and what we understand. Some force we have barely begun to comprehend, a force that comprises most of the universe, a force that is tearing everything apart. That force has a name, dark energy, and it accounts for 68% of everything that exists. Not 68% of matter, 68% of the entire universe. All the stars you can see, all the galaxies Webb has catalogued, all the planets and moons and asteroids and cosmic dust, everything made of atoms. That represents roughly 5% of what exists. Dark matter, the invisible scaffolding we discussed earlier, comprises another 27%. The remaining 68% belongs to dark energy. We cannot see it. We cannot touch it. We cannot detect it directly with any instrument ever built. We only know it exists because of what it does. It pushes. It stretches space itself, and it grows stronger every moment. And here is where dark energy becomes truly strange. When normal matter spreads out, it gets thinner. Picture a cloud of gas expanding into a larger volume. The same amount of gas now fills more space. Its density drops. The gas becomes more diffuse. This is how everything else in the universe behaves. Expansion dilutes matter. Dark energy does not work this way. As space expands, the density of dark energy stays exactly the same. Not almost the same, exactly the same. Every cubic meter of space contains the same amount of dark energy, whether the universe is young and small or ancient and vast. the same amount per cubic meter. Always. Think about what this means. Consider a box of space, any size. It contains a certain amount of dark energy. The universe expands. The box is now larger, and it still contains the same density of dark energy per cubic meter. But there are more cubic meters now. More space means more total dark energy. It resembles an engine that gets more powerful the faster it runs. Every bit of expansion creates new space. Every bit of new space creates more dark energy. More dark energy drives more expansion, which creates more space, which creates more dark energy. The cycle feeds itself. This is not merely an oddity of mathematics. It determines the fate of everything. In the early universe, matter dominated. Galaxies pulled toward each other through gravity. The cosmic web formed. Clusters coalesced at the nodes. Expansion continued, but gravity fought back, holding structures together, building complexity from simplicity. Matter was winning. Then something changed. Around 5 billion years ago, dark energy began to dominate. The universe had expanded enough that matter had diluted significantly. Stars and galaxies were spread thin across vast distances, but dark energy's density never dropped. At some threshold, the outward push of dark energy exceeded the inward pull of gravity. Expansion began to accelerate. We are living in that era of acceleration right now. The space between galaxy clusters is growing faster than it was 1 billion years ago. 1 billion years from now, it will be growing faster still. The engine keeps feeding itself. For now, gravity still holds local structures together. The Milky Way remains bound. Andromeda still approaches. Our local group of galaxies orbits as a single system. The internal gravity of these structures exceeds the expansive push of dark energy at close range. We are safe inside our gravitational island. Distant clusters are another matter. They are already receding from us at increasing speeds. Eventually, they will cross beyond the point where their light can ever reach us. They will vanish from our observable universe forever. Not because they moved away through space, because space itself carried them beyond our horizon. But what if dark energy does not remain constant? What if its density increases over time? Current observations suggest dark energy's density stays fixed, but observations have limits. We cannot measure its behavior with perfect precision, and some theoretical models suggest dark energy might strengthen as the universe ages. If it does, the consequences become catastrophic. Scientists call this scenario the Big Rip. It begins slowly. Galaxy clusters drift apart faster than they already do. The cosmic web stretches. Filaments thin and break. The great structures that took billions of years to form begin to dissolve. Clusters that once held thousands of galaxies find their members scattering into the void. Then, individual galaxies feel the strain. The Milky Way, Andromeda, every spiral and elliptical across the cosmos. Dark energy's push overcomes the gravity binding their stars together. Galaxies begin to unravel. Stars drift apart like leaves on a river. The process continues. Solar systems feel the force. The gravity holding planets in orbit becomes insufficient. Worlds drift away from their stars. Moons separate from their planets. Everything that once orbited now wanders free. Then, planetary bodies themselves begin to break. The chemical bonds holding molecules together, the electromagnetic forces that give matter its structure, all of it becomes weaker than the expansion of space itself. Planets crumble. Atmospheres disperse. Rock becomes dust. In the final moments, atoms cannot hold themselves together. The force binding electrons to nuclei breaks. Protons and neutrons tear apart. The expansion that began so gently, so imperceptibly, in the first fraction of a second, after the Big Bang, ends by ripping reality apart at the subatomic level. Everything that ever existed, every star that ever burned, every civilization that ever wondered at the night sky, reduced to scattered particles in an expanding void. No structures, no complexity, no light, just fundamental particles drifting forever through infinite empty space. This may not happen. Current measurements suggest dark energy remains constant, not strengthening. The Big Rip requires dark energy to change in ways we have not observed, but we do not understand what dark energy actually is. We do not know why it exists. We do not know why its density takes the value it does. We do not know if it has always been constant, or if it has changed in ways too subtle for our instruments to detect. We call it dark energy because we cannot see it. The name describes our ignorance more than the phenomenon itself, and yet, this invisible force comprises most of what exists. It determines how the universe ends. It shapes the ultimate fate of every structure, every galaxy, every star, every atom. Now, the thing we understand least controls the outcome of everything. For now, the engine runs quietly, space expands, dark energy accumulates, the acceleration continues. Distant galaxies slip beyond our reach one by one. The observable universe grows emptier by the cosmological year, and as dark energy pushes space apart, something strange happens to time itself. Something strange happens when you follow dark energy's logic to its end. Space keeps growing, the expansion keeps accelerating, and eventually, the growth of space itself begins to outpace something we thought could never be outpaced. Light, the fastest thing in existence, the universal speed limit, the cosmic constant that Einstein built his theories upon. Light travels at 186,000 miles every second, and nothing that moves through space can exceed this speed. No spacecraft, no signal, no particle. This law has held for over a century of testing. And yet, right now, at this very moment, galaxies exist that are receding from us faster than light can travel. They are moving away from Earth at speeds that exceed that sacred limit. This sounds impossible. It sounds like a violation of everything physics holds true. But it is not a violation. It is completely legal, confirmed by science. The distinction is subtle, but everything depends on it. Einstein's speed limit applies to objects moving through space. A rocket cannot travel through the vacuum faster than light. A photon cannot be overtaken by anything with mass. Nothing that exists within space can break this barrier. Space itself, however, follows no such rule. Space is not an object. It is not a thing moving through something else. Space is the something else. It is the stage upon which all motion occurs, and that stage can expand at whatever rate the universe demands. There is no speed limit for the growth of emptiness. Picture this. Imagine someone running toward you on a treadmill. They are sprinting as fast as they possibly can. Their legs pump, their arms swing. Every muscle strains toward you. They are giving everything they have. Now imagine the treadmill begins to speed up. The belt beneath their feet moves faster. They keep running. They do not slow down, but the treadmill accelerates. Soon it matches their running speed. They sprint in place, neither approaching nor retreating. Then the treadmill speeds up more. Despite running forward at full speed, they begin moving backward, away from you. The belt beneath them carries them away faster than their legs can compensate. They are still running toward you. Every step they take is aimed at reaching you, but the ground itself defeats them. This is what happens to light from distant galaxies. Photons leave those galaxies aimed directly at us. They travel at the maximum possible speed. They have been racing toward Earth for billions of years. They never slow down. They never tire. They cross the void at 186,000 miles every second, never wavering. But the space beneath them keeps expanding. The cosmic treadmill keeps accelerating. And for galaxies far enough away, the expansion wins. The photons run toward us forever without ever arriving. This creates a boundary, a line in the universe beyond which light can never reach us. Not because something blocks it, not because the photons stop, but because the space they must cross grows faster than they can travel, beyond the cosmic horizon. That phrase describes something real, a spherical shell surrounding us in every direction. Everything inside that shell can eventually send light that reaches Earth. Everything outside that shell cannot. The photons from those regions are running on a treadmill that will never let them arrive. The horizon is not a wall. It is not made of matter or energy. You could not touch it or see it. If you traveled to where the horizon exists today, you would find nothing special. Just more space, more galaxies, more stars. But from Earth's perspective, that boundary marks the edge of everything we can ever observe, everything we can ever know through light, everything that can ever communicate with us across the void. And here is what makes it stranger still. Galaxies that we can see right now, galaxies whose light reached Webb's instruments, are currently beyond this horizon. The light we observe left them billions of years ago, when they were close enough for their photons to reach us. But during the time that light traveled, space kept expanding. Those galaxies kept receding. The objects we photograph already exist in a place we can no longer reach. Their present location lies beyond the cosmic horizon. The light leaving them now will never arrive here. We see their past. Their present is already gone to us. Yes, their future will be forever unknown. This is not a limitation of our technology. Building a bigger telescope cannot help. Waiting longer cannot help. The photons simply will not arrive. The treadmill is too fast. The cosmic horizon does not care about human ingenuity. Space can do whatever it wants. That is the uncomfortable truth hiding inside Einstein's equations. His speed limit governs motion through space. It says nothing about the behavior of space itself, and space, driven by dark energy, has chosen to grow without limit. Every second, that growth continues. Every moment, the horizon claims more territory. Galaxies that were once reachable slip beyond the boundary one by one. Their light runs toward us on an accelerating treadmill. It will run forever. The universe plays by rules we never imagined. Our objects recede faster than light without breaking any law. The speed limit remains intact. Physics holds. But the loophole changes everything. We live inside a bubble. The edge of that bubble is not physical. It is mathematical. It marks the point where expansion equals the speed of light. Everything beyond that boundary races away too fast for its light to reach us. The boundary exists right now, surrounding us, defining what we can see, and as dark energy pushes space to expand faster, that boundary affects everything beyond our local neighborhood. The galaxies we observe tonight are sending light that started its journey before this acceleration grew so strong. Ancient light that left when the treadmill ran slower. Those photons managed to reach us because they had a head start. Newer light does not have that advantage. Beyond the cosmic horizon, the universe continues. Galaxies spin, stars burn. Perhaps civilizations wonder about their own horizons, but their signals will never cross the growing void to find us. Our signals will never find them. The treadmill runs in both directions. Consider those galaxies drifting toward the edge of what we can see, the ones whose light still reaches Webb's golden mirrors. As they approach that invisible boundary where expansion equals the speed of light, something peculiar happens to how we perceive them. Their clocks appear to slow down. Their stellar explosions seem to take longer. Their entire existence stretches out like a single moment caught and held. From Earth, these distant galaxies look frozen, like insects in amber, caught in a single instant of cosmic history while billions of years flow past us here. A supernova that should flash and fade in weeks seems to linger for months, then years. The spinning of their stars appears to crawl. Every process, every motion, every heartbeat of their existence slows towards stillness as they drift closer to that threshold. This is not an optical illusion. This is not some trick of tired telescopes or faulty instruments. This is space-time itself, bending the rules of what time means. The light from these galaxies gets stretched, not just in wavelength, not just in the colors it carries, but in the information it holds about when things happened. Each photon becomes a messenger carrying news that arrives later and later and later, until eventually the news stops arriving at all. Picture a radio signal slowing down, each word taking longer to reach you than the last. First, a pause between sentences, then a pause between words, then between syllables, until finally the speaker seems frozen mid-sentence, their voice stretched into an eternal hum that never quite becomes the next sound. That is what we see when we look at galaxies near the cosmic horizon. Time itself appears to stop, but here is where the universe reveals its strangest symmetry. From their perspective, nothing unusual happens at all. Their clocks tick normally. Their stars spin at their ordinary pace. Their civilizations, if they have any, go about their business without any sense that time has changed. To them, everything flows the way it always has. We are the ones who appear frozen. If an astronomer in one of those distant galaxies pointed their instruments toward us, they would see the Milky Way caught in amber at the edge of their observable universe. Our time slowing, our signals stretching, our entire existence appearing to crawl towards stillness while their world spins on. The isolation works both ways. Beyond the cosmic horizon, in every direction, There are galaxies we will never contact. Their radio signals will never reach us. Not because they are not transmitting, not because their technology failed, but because the space between us grows faster than their messages can travel. Those signals are out there right now, crossing the void, running toward us on a path that will never end. Our signals face the same fate heading toward them. Two ships sailing in opposite directions, each equipped with radios powerful enough to span oceans. At first, they communicate freely, voices clear across the water. But as they drift further apart, the signals grow fainter. Static creeps in. Words become difficult to make out. Eventually, no matter how much power they pour into their transmitters, the messages stop arriving. The ships are still there, still broadcasting, still listening, but they have passed beyond each other's reach. That is the radio silence of the cosmos. Not empty space where no one exists, but crowded space filled with voices that can never hear each other. The strange part is not that we are isolated. The strange part is that the isolation is perfectly mutual. We look out and see galaxies frozen at the edge of our vision, their time crawling to a stop. They look out and see us the same way. And two perspectives, each convinced the other has slowed while they themselves tick along normally. Neither is wrong. Both are right. That is what space-time does to perception across cosmic distances. So somewhere out there, in a galaxy, we can still see, but will never contact. An alien astronomer might be giving a presentation about the strange frozen galaxy called the Milky Way, caught forever in some distant past, its inhabitants never to know they are being observed. They might wonder what kind of life existed there, what kind of thoughts those creatures had before their time stopped, and they would be just as right about us as we are about them. The amber holds us both. This creates something difficult to hold in your mind. Separate pockets of existence, each flowing through time, normally from the inside, each appearing frozen from the outside. Not one correct frame of reference, and one illusion. Both equally real, both equally true. The universe does not prefer our perspective over theirs. It does not grant us the true clock, while they experience the distorted one. Time bends for everyone, depending on where you stand. The photons still traveling between these distant shores carry information about moments that will never quite arrive, stretched longer and longer, shifted further and further toward invisible wavelengths, until they fade below any instrument we could ever build, not because they stopped existing, but because they stretched into silence. Beyond the cosmic horizon, the universe continues without us. Stars ignite, planets form. Perhaps civilizations rise and fall and rise again. All of it happening at a normal pace from their perspective. All of it forever invisible from ours. And somewhere in that invisible expanse, someone might be looking toward where we are, watching our frozen image, wondering if we ever wondered about them. The amber is clear, but it holds us all the same. The amber holds us all the same. But what lies beyond it? We have spent this journey mapping what we can see. The galaxies, the filaments, the voids, the ancient light stretched thin by expansion. All of it contained within that sphere we call the observable universe. All of it bound by the distance light has managed to travel since the beginning. But that boundary is not a wall. It is not an edge where space stops existing. It is simply the limit of what we can know. The place where information runs out. Beyond it, the universe continues. And the question that haunts cosmology is simple. How far does it continue? The geometry of space tells us something profound. When astronomers measure the angles of cosmic triangles, triangles formed by distant points of light separated by billions of light years, those angles add up to exactly 180 degrees. Every time, without exception. This means space is flat, not curved in on itself like the surface of a sphere, not warped into some exotic shape that might loop back around. Flat geometry carries a consequence most people never consider. If space were curved, it might close in on itself. You could travel far enough and end up where you started. The universe would be finite, just very large. But flat geometry has no such closure. Flat geometry extends without limit. The mathematics suggests the universe is infinite, not metaphorically infinite, not poetically infinite, mathematically, physically, actually infinite, stretching in every direction with no boundary, no edge, no place where space gives way to something else. Consider what this means. Everything we have discussed, every galaxy Webb has photographed, every void it has mapped, every ancient structure that defies our models, all of it exists within a region smaller than a drop in an ocean that has no shore. The observable sphere spans those many billions of light years we have measured. It contains everything science has ever studied, every star humanity has named, every world we have imagined visiting. And if the universe is truly infinite, that entire sphere occupies precisely 0% of the total. Not a small percentage, zero, because any finite number divided by infinity equals nothing. Picture a fishbowl floating in an endless sea. The glass is perfectly clear. The fish inside can see every corner of their world with complete precision. They have mapped the pebbles on the bottom. They know where the plants grow thickest. They have catalogued every bubble rising through the water. Their fishbowl is their universe, and they understand it well. But the ocean extends forever in every direction. Beyond the glass, currents flow that the fish will never feel. Creatures swim that they will never glimpse. Entire ecosystems exist, flourish, change, and vanish without any effect on life inside the bowl. The fish cannot see the ocean, cannot detect it, cannot even imagine what form it takes. Their entire reality, every discovery they have made, represents a volume so small compared to the whole that it essentially does not exist. That fishbowl is us. That ocean is the universe we will never reach. Let this settle into your thoughts. The sphere of light that defines our cosmic horizon contains wonders beyond comprehension. Trillions of galaxies, quadrillions of worlds, structures spanning hundreds of millions of light years, and all of it, the totality of everything we can ever observe or measure or visit, may be an infinitesimally small sample of what actually exists. Most of reality lies permanently beyond our reach, not because we lack the technology to see it, not because we need better telescopes or faster ships, but because the light from those places will never arrive. That the fabric of space between us and those distant regions grows faster than any signal can cross it. They are there. They exist. Galaxies spin, and stars burn, and perhaps civilizations rise, but we will never know anything about them. Not now. Not ever. There is something else worth holding in this moment. Something about timing that verges on the miraculous. We happen to exist in a particular era. The universe is old enough that light from the most distant visible galaxies has reached us. Those photons began their journey when the cosmos was young, and they have been traveling ever since, arriving just as we developed the instruments to receive them. We can look back across time and witness the universe assembling itself. But the universe is also young enough that those distant galaxies have not yet disappeared. Oh, they still hover at the edges of our vision. Their light still crosses the void, stretched thin but present. We can study them, learn from them, understand where we came from. Future observers will not have this privilege. As expansion accelerates, distant objects will cross the horizon and vanish. Not dramatically, not suddenly. They will simply redshift further and further, their light stretching until it carries no detectable energy. From the perspective of astronomers in the deep future, those galaxies will fade like whispers trailing into silence. Eventually, trillions of years from now, observers will look up and see only nearby stars. The wider universe will have disappeared entirely. No evidence that it ever existed, no ancient light revealing the cosmic web, and no record of the structures that once stretched across billions of light years. Just a small island of stars in what appears to be an endless, empty void. Those future astronomers might conclude that their galaxy cluster is all there is. They would have no reason to suspect otherwise. The light that could have told them the truth will have stretched beyond detection, its message erased by the passage of time. We stand at a window that is slowly closing, not in our lifetimes, not in the lifetime of our species, but closing nonetheless. The view we have now, the cosmic perspective Webb and its successors reveal, this is a temporary gift, a snapshot of an era when the universe still chose to show itself. We are not special in our location. Earth holds no privileged position in space, yet we orbit an ordinary star in an ordinary galaxy in an ordinary cluster. The cosmos does not arrange itself around us, but in time, we may be extraordinarily lucky. We exist during the brief window when the universe's autobiography remains readable, when the chapters have not yet faded from the page, when the light still arrives carrying stories of what came before. Someday, that window will close, the stories will fade, and whatever observers remain will never know what they missed. The window closes slowly, so slowly that no single generation will notice, but the closing is inevitable. In approximately 150 billion years, the last light from distant galaxies will fade beyond detection, not because the galaxies die, not because their stars burn out, but because the space between us and them will have grown too vast for any signal to cross. Think about what that means. Every galaxy not gravitationally bound to our own will drift past an invisible threshold. Once crossed, no light, no radio wave, no message of any kind can ever return. The objects themselves continue to exist. Stars still burn, planets still orbit, perhaps life still flourishes, but from our perspective, they vanish completely, as if they were never there. The cosmic microwave background will go first, that faint glow permeating all of space, the afterglow of creation itself. Right now, we can detect it from any direction we look. It tells us the universe was once hot and dense. It tells us expansion began from a single point. It tells us how old everything is. But that glow is already stretching, already fading, and eventually, it will stretch beyond any instrument's ability to detect. The whisper will become silence. Consider what happens next. The merged galaxy that was once the Milky Way and Andromeda will hang alone in the void. Surrounding it will be absolute emptiness. Not the emptiness we know now, punctuated by distant points of light. True emptiness. Complete. Eternal. No other galaxies visible in any direction. No microwave background painting the sky. No evidence that anything else ever existed. It is as if the evidence of the universe's birth is being slowly removed from the scene. The cosmic microwave background served as the smoking gun of the Big Bang. Future scientists will never find it. The distant galaxies that proved expansion happened at all will have departed beyond the cosmic horizon. Future telescopes will search the sky and find nothing but their own local stars. This is not a failure of technology. Future civilizations might build instruments far more sensitive than anything we can imagine. They might have telescopes spanning entire solar systems. It will not matter. The evidence will have physically departed from the observable universe. No amount of ingenuity can recover what has crossed that threshold. The implications are haunting. Future astronomers will look at their data and reach completely wrong conclusions. They will see a single galaxy surrounded by void. They will measure no expansion because there will be nothing left to measure expansion against. They will find no relic radiation to hint at a hot beginning. They will likely conclude they live in an island universe, at a single collection of stars floating alone in infinite, static, empty space. They will develop physics to explain this reality. They will build models that work perfectly within their limited view, and every one of those models will be wrong. Not because they are bad scientists. Their methods will be rigorous. Their mathematics will be precise. Their conclusions will follow logically from the available evidence. The problem is that the evidence no longer exists. The truth of the cosmos will have passed beyond the cosmic horizon, and no amount of brilliance will bring it back. We don't know if intelligent life will still exist in 150 billion years. We don't know if anyone will be there to observe this emptiness, but if they are, they will never know what we know. That is a strange kind of loneliness. We hold something precious, a view of the cosmos that reveals its true nature. We can trace the expansion backward. We can see the web of galaxies stretching across billions of light years. We can detect the faint warmth left over from the beginning of everything. We know we are not alone in an empty void. We know the universe is vast and structured, and ancient and still growing. Future observers will inherit cosmic amnesia. The universe will have erased its own history, not maliciously, not deliberately, just inevitably. And the expansion that reveals the cosmos to us now will eventually hide it from those who come after. The evidence fades even now. With each passing moment, light from the most distant objects stretches a little further, reddens a little more, grows a little fainter. The horizon creeps closer. The autobiography of the universe loses another page. And someday, no pages will remain. The pages are gone, the story erased. And still, something remains. You, here, now, breathing on a world that orbits an ordinary star, a star among hundreds of billions in a spiral galaxy that looks like countless others. Your galaxy drifts through a cluster that resembles every other cluster. Your cluster clings to a filament that could be any filament in the cosmic web. Nothing about your address is special. Nothing about your location stands out. You are nowhere in particular. A speck of awareness on a cooling rock in an unremarkable neighborhood of an indifferent cosmos. That is the truth of space. But time tells a different story. Right now, at this exact moment in cosmic history, the universe still shows its hand. The ancient light still arrives. The microwave glow still paints the sky. The web of galaxies still stretches across the darkness where instruments can find it. You are standing at a window. Through it, you can see everything. The first structures forming, the filaments taking shape, the dance of matter across billions of years. The universe has left its diary open on the table, and you happen to be in the room. The window is closing. Not quickly, not in any way you would notice, but inevitably. And with each heartbeat, the frame narrows slightly. The view contracts. The most distant stories slip past the edge and vanish. In the span of cosmic time, this window will be open for only a breath, a flicker of an instant when the full narrative remains visible to anyone looking up. Before this moment, the universe was too young to reveal its structure. After this moment, the universe will be too old. The evidence will have departed. The cosmic microwave background will stretch beyond detection. The distant galaxies will accelerate past the point of no return. There is only now. Your physical insignificance could not be more complete. Dust on a speck in an average corner of an average spiral. The cosmos would not notice your absence. The web would continue without a single filament disturbed. And yet you exist at the one moment when all of it can still be seen. The telescope floating in the cold dark points its golden mirror outward and captures photons that started traveling before planets existed. Those photons complete their journey and land on instruments built by the very dust the cosmos forgot to notice. That dust built eyes to see, built minds to understand, built machines to extend that seeing across billions of years. The universe created something that could look back at it and comprehend the view. You are not special in space. You are profoundly rare in time. Somewhere, in some distant future, intelligent beings may arise who will never know what you know. They will look up at empty skies and conclude they are alone. They will be wrong, but they will never discover their error. And the evidence will have departed long before they opened their eyes. You hold what they will never find. The James Webb Space Telescope drifts through the darkness, 1,000,000 miles from home, gathering the last light from the universe's open window. It shows you the cosmos at the one moment the cosmos is still willing to be shown. That might be everything.